and take over.
Thank you very much, Tobias, for the warm welcome and for giving me a chance to speak today. So I'm talking about explainable AI in medical image analysis. So let's see if I can keep the promises of my title. So I will talk about XAI promises, then a reality check, and ways forward. So we've all seen a lot of news about AI in general in the media, but also AI in medicine specifically. And there have been a lot of articles out there demonstrating that AI in many cases is matching or even surpassing expert performance on some tasks and in some settings. For example, in detecting pathologies on chest X-ray images or image segmentation, etc. And then there's also, of course, the whole area of generative AI, which I will actually not talk about today. And indeed, so to address the question whether AI is ready for deployment in healthcare settings, we can have a look at the number of FDA-approved medical AI devices, and there are many out there already. So since about the rise of deep learning around 2016, 17, we've seen also an exponential growth in approved medical AI devices, most of them in radiology, but also in a lot of other areas, for example, in ophthalmology. However, I have some examples here. So this is one example of a medical AI device where diabetic retinopathy is detected actually autonomously without a human in the loop. So basically, an image is acquired of the retina, of the back of the eye, and then you get basically yes or no, is there diabetic retinopathy present in an early stage in that patient. Just to give you a little bit of background, so there is always in medical devices, there's an intended use that has to be followed strictly. So here, for example, the approval is restricted to a specific camera type, a device by Topcon, and it's also restricted by image quality. So the images should be of good enough quality, and it's only intended for use by people older than 22 years of age and not pregnant. So there's this kind of boxing in the plausible or the population where this algorithm can be applied. There's another example here on breast cancer screening where we have a machine learning algorithm as an additional reader. So this is a human AI collaboration. So we have the mammography image, and then there's this, I'm not going through this in detail, but then there's this reading procedure where you have two readers, usually human, and then there's the possibility of inserting AI as an additional reader. This is also approved, and it has been shown that using AI here results in 12% more positive cases being detected without actually adding a lot of additional false positives. So this is also commercially available. So yes, there are medical AI devices out there that have been demonstrated to be safe and effective. However, especially in a healthcare setting, AI errors have consequences, and these can be minor for a patient. So this could lead to inefficiency. So errors could lead to financial cost or time lost. So this is not considered patient harm, but errors in diagnosis may also actually lead to patient harm. For example, a false negative diagnosis may lead to delayed treatment or no treatment, increased morbidity, and in the very worst case, death or premature death. Whereas also false positives have consequences. So this could lead to overtreatment. So if you say that there is something there and then maybe you need to take a biopsy, etc. So there's a lot of mental and physical burden, and it can affect the quality of life of the patient. So that's the reason why medical AI devices or machine learning algorithms that get applied for to treat or to diagnose or to assess patients are medical devices, and they are regulated as such. And a big part of medical device development is basically risk management. So with all the possible things that could go wrong, you need to have a list of things that could go wrong, and then a list of mitigations how to address this. So we do have, on the one hand, this amazing opportunity of this disruptive performance of modern machine learning, deep neural networks. But then we have all of the real world risks when deploying AI. So it is entirely possible, and it happens, that machine learning predictions are silently wrong. This can happen, for example, when the real world data is different from clinical validation data. So it could be that maybe the imaging devices are slightly different or drastically different. Maybe the patient population is different. And we know that whenever machine learning, the data used by machine learning is somehow, not exactly overlapping with the training distribution, then we just cannot rely on performance claims. We may also deal with heterogeneous data quality, and not a minor factor is that the system may just be used incorrectly or not in the way that the developer intended. So we have all of these mitigations, and on the technical side, the mitigations for these real-world risks is the whole field of trustworthy AI. So this could mean that we need to develop outlier detection techniques to detect when an image that is used as an input for an algorithm is not maybe from a device that was not included in the intended use. This could mean that we need to make our algorithms robust to low quality data. It could mean that we implement uncertainty quantification technique to be able to assess when the system might be uncertain or unsure. It might mean that we develop input and output monitoring systems. And one important aspect is model interpretability. So we might want to develop models that are interpretable so that we can inspect them. Or it might mean that we might want to develop explainability techniques to examine a black box algorithm post hoc. So I have a quote here by Cynthia Rudin, who is a famous computer scientist who has done a lot of excellent work in the area of interpretable machine learning. And she says, I don't think we should permit black box solutions for high stakes decisions. There should be some exceptions, for example, when we know that the AI is 100% accurate, or when there is no way to create an interpretable system. And she's not the only one. She's, of course, a very prominent person in this field, but there are many voices that ask for interpretability in high-stakes situations. And we will have a closer look at this now. So here you see an example of just some schema of a machine learning algorithm that takes as an input a chest X-ray image, then gets passed into an opaque, highly nonlinear function, and then there is some output whether this patient has a disease or is healthy. And we might want to unwrap this black box here. And the reason is that transparency in high-stakes applications might mean that we want to trust the system, because trust affects also downstream decisions, so treatment decisions, for example. Interpretability also aids the inspection and certification of a machine learning algorithm. And anyway, also interpretability is mandated by, for example, by the GDPR, the data protection regulation. And apart from regulations, there is a very strong sense that having interpretable machine learning models also builds social trust that is really necessary for the adoption of AI. So what could this mean? Mostly, especially in medical imaging, when we talk about model interpretability, we are talking about visual explanations. So again, we have our chest X-ray image, we have our black box algorithm, for example, let's say it's a black box, and then this algorithm can detect different pathologies, for example, airspace opacities, pleural effusion, or the presence of support devices in this image. But then along with the decision, whether this is present or not, there is some sort of saliency map, some sort of heat map that shows which areas of the image are used by the machine learning algorithm to make its decision. So where is the evidence for this class here? There's many types of saliency maps, but many of them are actually post hoc explanations of deep neural networks. So the algorithm itself is not interpretable. It's a very highly nonlinear function, but we find some approximations of this function here that will allow us to see where the algorithm looked for its decision. And this is appealing for several reasons. So, I mean, this is just something that is obviously appealing, right? You can see, you cannot really see what happened, but you can at least see which areas were important. And we will talk more about how this can be useful and where this might not necessarily actually be so useful. So here we have one, I think, very attractive use case of visual explanations. So what can happen is that we have an algorithm that is supposed to detect something on an image, for example, here on chest X-ray images. And in this case, in this example, what we want to detect is cardiomegaly, an enlarged heart. So we can develop an algorithm. It can have excellent performance on our test data, but we don't really know what information was used by the algorithm, right? What happens in this case and what can happen in reality is that there are some sort of artifacts in our image. And here in this work led by Susu-san, we actually introduced these artifacts artificially. So we have hyperintensities, so these hyperintense lines, vertical lines here. We also have hospital tags that can just be placed by the acquisition system, or there could be some obstruction, so this oblique, this triangle here. And what can happen is that these artifacts are somehow spuriously correlated with the disease itself. So for some reason, it could be that we include cardiomegaly patients from maybe a setting where there are more hyperintense lines. And then we include the healthy cases from a scanner or from a setting where we don't have these artifacts. So that the artifacts are then correlated with the thing we are trying to predict. And this is, of course, not desirable behavior. So what we can do is we can train a black box classifier and then use post hoc or use saliency maps to see where the model looked to make its decision. And in this case, we can see, so this is a method developed by Susu, that actually the decision was based on these lines. Or here for the obstruction here, we can very clearly see this area highlighted here. So again, clearly faulty behavior that we could expose through the use of visual explanations. The same here. So here we have this hospital tag here that is spuriously correlated with cardiomegaly, with the disease we are trying to detect. And we see again, it's highlighted here in the explanation. So clearly the model learned a shortcut, so the artifact here, instead of the actual disease features. So this is, I think, an area where explainability is extremely useful. However, what we can also see is this was just one approach to get these explanations. But there's a lot of different ways to get visual explanations. And we can see with these other types of saliency techniques, the picture is completely different. So every approach to explanation leads exposes something completely different. So I mean, I really don't see any patterns here. And this really means that, so the explanations, they depend on the explainability technique, which means that they don't really explain the model itself, or not only, but there's some component of the XAI as well. And one difference between this here on the right, that in this case works quite reliably, that's what it was intended to do, is that this is actually an inherently interpretable technique, whereas these here are post hoc explanations. So they actually they use a black box model that they then explain later. So the model itself is opaque, and then there's different approximations to try to guess. Maybe guess is not so generous, but there's just different approaches to approximate this decision. So we cannot fully trust visual explanations usually, even though they do have some very appealing properties and people really like to use them. So we saw here that this inherently interpretable technique, its explanation shows really the mechanism. It really shows which areas were used. So this is quite reliable. So in my own research, we did quite a lot of that. So we tried to make machine learning or deep learning algorithms inherently interpretable so that we can understand the mechanism of the algorithm, rather than using black box classifiers with post-hoc explanations. And here we have an example of a really nice project, I think, led by Carol Ciumessi. And this is an inherently interpretable model for diabetic retinopathy detection. So similar to the application that we saw before. So here we take retinal fundus images, so images of the back of the eye. These are routinely acquired in people with diabetes because many of them will eventually develop retinal complications. So they often go for these eye scans. And then the clinician will search for tiny lesions, basically. I think I have some examples later of these tiny lesions. And this is a task that can be solved relatively well with machine learning. And as you saw in the beginning, there are already approved devices out there. So what we did is we took a neural network, kind of a classical convolutional neural network, but we modified its architecture slightly so that we end up with a heat map as part of the network architecture, where every part of the heat map basically corresponds to a part of the input image. And this heat map is actually a directly disease evidence map. And we through the model architecture, we really control that whatever is highlighted here can only come from this region here. And then the final decision is really just a simple aggregation of this evidence here. So what we get is some output. Is there diabetic retinopathy or not? Along with the heat map that is really faithful to the model. And what we can also do is we can, based on these highlighted areas, we can then extract the patches from the input image and we can inspect them, or the clinician can inspect them. So this is actually on a technical level relatively simple, just some minor modifications, but the implications for interpretability were quite nice. And what we often have with interpretable techniques is that there is some sort of trade-off between performance and interpretability. So in this case, if we look at, so we have here the interpretable model and the black box model, and we can see that there is some performance drop. So there is some trade-off, but the performance is relatively okay. So we argue we can accept a slight performance drop if we get interpretability instead. And we also did some extensive external validation on a lot of different and also geographically diverse data sets, and just to make sure that the model also performs in different data. And I mean, there's, I would say generalization is okay. It's not perfect. It also depends a lot. So these data sets are very different from each other. But it seems somewhat robust. And then I already hinted at this. So we get, with every machine learning prediction, we get these heat maps. We directly also get these patches that show high disease activity. And what we can see here, you see these tiny dots here? These are actually the microaneurysms that are the earliest signs of diabetic retinopathy. So with these kinds of explanations, we thought this could make it quite easy for clinicians to debug the system, basically, to see whether the explanation or whether the model decision makes sense or not. And we validated that with clinicians. So we had them annotate the lesions, and we saw that there is like all of the, not all of them, but most of the areas highlighted by the algorithm actually contained such a lesion. But then we thought, okay, so we have this interpretable model. We like it, you know, in the machine learning community, we can argue that it makes sense, but how do we evaluate whether it makes sense in a clinical setting, whether it's actually useful for a human? You know, we have this human here. So we did a clinical study to see what the performance of the AI-assisted clinician is. We did this not actually in the clinic, so it's a little bit removed, but we conducted a survey where we had a number of images, and we had this questionnaire where we asked the clinician, so we had a pool of clinicians here, does the patient have diabetic retinopathy, including mild diabetic retinopathy? And they basically had to answer yes or no, and how confident they were. So this is just their usual task, right? But then we also gave them, in addition, the model prediction. So they now had their own, they could do their expert assessment, but then also the model assessment. And then in the third case, we also provide them the model prediction, but we also provide them with the explanation. And then here you don't see it so well, but here they would have a magnifying glass. And then we wanted to see whether this these explanations actually helped the clinicians in any way. So we did this on 6 ophthalmologists with a range of experience. And what we found is that going from human to human plus AI to human plus XAI, that their accuracy, so the accuracy of the system, the human plus AI system, actually improved. So there's not such a big improvement with the explanations versus only with the AI. It's a slight improvement. What we did see is that the time required to make a decision was reduced drastically. So the explanations really helped the clinicians make a decision fast. And then what we also saw is that, especially for the difficult cases, so here we have the diabetic retinopathy grade. So this is healthy, and then this is early, mild diabetic retinopathy, and then this is moderate. So these are the difficult borderline cases. And here we saw that the explanations really help to distinguish between well, healthy and disease. So this was really nice work done by Carol, and I think it went an early step in the direction of kind of breaking away from this AI developer perspective, where we usually just think about, you know, an image, a machine learning model, and some model output. Whereas what happens in reality is that there is some clinical workflow. So we have the image acquisition, then maybe we have a triage system, and then based on this triage, the clinician will read the images, and then there will be some final assessment. And there are various steps here where AI could be applied. So the application setting really is not always the same. So it could be that you have a fully autonomous system where actually the final assessment is done directly by the AI. It could be that AI is used for triaging, or it could be that AI is used, as in this study setting that we explored, that the AI is used to aid the clinician directly in their reading of the image. So so this application setting, of course, this also influences who even interacts with the model and who would even see the model explanation, right? If we have some visual explanations and it's done for triaging and nobody looks at the output there, then the explanation is worthless. So we have to consider who interacts with the AI. Is it a technician? Is it a radiologist? Is it a patient? Does the patient require an explanation? Is it maybe a regulator? Or does nobody ever see the AI output because it's fully autonomous? So that means that interpretability is not actually always useful or even applicable. And also, just having developed some explainability technique does not automatically answer the question how this interpretability or how this explanation actually establishes trust. And also, it's not immediately clear with whom does it establish trust, with the regulators, with the operators, or with the patients. And I mean, I'm not answering that question. I'm just saying it's an important question to ask. But now I want to move on to the second part of today's talk, where I want to make the case that interpretability is not actually the only facilitator of trust. So I think people ask for explainability and interpretability a lot, but it's not. There's other ways to get trust, and for that there is this debate where you could say, as a patient, I don't need to understand exactly how a drug works, for example, to trust the clinician's prescription. So why do we need AI to be explainable when we don't really ask that for other very critical applications like medication, for example? There's a bit of a fallacy there. So regulators actually do require an understanding of the drug mechanisms. So they do require some form of interpretability. So it's not, the argument doesn't completely make sense, but I think it makes sense to an extent. And then the other thing I want to say here that I think if people want explainability, then they need explainability, right? So if that's needed to establish trust and to aid the adoption of AI, then I think that's a clear sign that we need to work on that. But then also, so regulators may require an understanding of the drug mechanisms for the case of drug development, but they also require extensive evidence of safety and effectiveness. So I think the reason why we may trust a clinician when they prescribe a drug, or that we take this drug without too much hesitation, is that we trust that it's safe and we trust that it's effective, not because we understand it, but because we trust the validation process. So I think a very, very important factor for trusting a machine learning model is trusting that it's been validated and that it's being monitored and that it really works for me. So I am coming back to this quote, and there's this middle sentence here, where Cynthia Rudin says, I don't think we should permit black box solutions for high stakes decisions. There could be some exceptions, for example, when we know that the AI is 100% accurate. So really, if I know I can trust it because I know it works, then I don't need to know more. So we can say that, validation and performance monitoring also is a form of providing transparency. So here I'm showing the medical device development lifecycle here on the right, which will probably help me trust that whatever machine learning algorithm is being applied to my data will actually work for me. So during the development phase is where you can improve your model performance and improve its robustness and maybe make it interpretable, etc. But then in the validation phase is where the manufacturer will provide clinical evidence that it works and establish performance claims. So how accurate is it? How sensitive is this algorithm, etc. But then the product is launched, then there is a requirement for post-market surveillance to monitor the actual real-world performance of a machine learning algorithm. And in both of these phases, actually in all of these phases, you can basically establish trust that the model will work as intended. It's not easy though. So we already talked about the fact that these most models are opaque. They lack inherent interpretability. This also means that we don't really fully understand the failure modes of deep learning algorithms. They are often deployed in very heterogeneous data. So you can see here, this is just a schematic, images from very diverse patient populations, maybe diverse acquisition settings. And then it also does happen that there are distribution shifts after deployment, which means that perhaps the system is not really within specifications, and the performance claims may not really be appropriate anymore, and they do not reflect the actual real-world performance. Another thing that can happen is that we report the performance of this system here, but actually there are some hidden performance gaps because there might be some hidden subpopulations that mean that the average performance may not reflect the systematic performance for this group or for this group. And to address this question, how well will this machine learning model actually work for somebody like me? We had a closer look at this, and one thing that is done to answer that question is traditional subgroup analysis. So you have a model, and then you report its performance, but you also report its performance in subgroups, in demographic subgroups, for example, male, female. You could report it in different age groups, hopefully in patients with different ethnicity, etc., to try to give a little bit of a more complete picture of the different subpopulations to assure that it will really work for all these groups. However, in reality, we have seen that whatever data you can acquire here is relatively limited in practice. And often these demographic subgroups, they don't really capture the real heterogeneity of our data. So it might be that something else actually drives performance, for example, image quality, which might not necessarily correlate with patient age, for example. So what we then did is, so we hypothesized that there are other factors like acquisition details. There might be some confounders, spurious correlations that we have seen before with these tags. So just overall, there might be just some hidden stratification in our data that lead to patient subgroups with different performance. And there are some data-driven approaches to discover subgroups. And that's what we did, basically. We used some sort of clustering technique to identify population subgroups and then did performance monitoring on those. So we didn't develop our own subgroup discovery technique. We used an existing model. It's a very popular one. It's called Domino. It basically, so you have the classification model that you're interested in, but then you also have some sort of feature extractor. And then with the machine learning predictions and with your image features, you run basically a clustering algorithm to identify your subgroups. And what we found is that, here you see the performance range of the different subgroups that were discovered. So you see that there is quite a range in accuracy. Here you have an accuracy of 60%, so very bad. And then most subgroups are somewhere in this range. But interestingly, looking at just the traditional subgroups, so the demographics, for example, that are available to us, you don't really see that range. So most performance variation comes from something else, something that we didn't measure in our patient population. So there are large performance gaps. They are hidden with traditional subgroup analysis. And the demographics do not really explain that. So we don't really know at this point what really causes them. But we do know, and we argue that this is something that can be very easily implemented. So this could be done during post-market surveillance, or it could be done during validation even. So we can identify patient subgroups. We can also try to work on explaining what their characteristics are, but we don't know at the moment. But with that, we can give some sort of patient-specific performance claims. For somebody like you, for somebody who lands in that subgroup, for whatever reason, you can expect the model to perform really, really good, or you can expect the model to actually fail very often. Yeah, so that is one thing. So this is an area where you can improve validation of machine learning algorithms to then as a facilitator of trust. There's another area, so you can also work on post-market surveillance. So in post-market surveillance of machine learning algorithms, you would often try to detect drifts in model performance or drifts in your data distribution. To answer the question, is the deployed model still within its specification? So can I still trust the performance claims, or is the model anyway diverging from the setting in which it was, for which it was approved? So this is also something that we work on. So what we have done here a few years ago is a detection technique to detect whether there is something different in our data. So we have our validation setting. This is where the clinical evidence emerges, and then we have the post-market setting where you have the real-world data. And what we want to see is whether so you see these blobs here are basically our data distributions, whether they are more or less the same between validation and post-market, or whether there is some sort of systematic difference. And that is something that is not so straightforward to do. Basically, you can think about developing a statistical test for seeing whether two distributions are different or not. But this statistical test needs to be performed on high-dimensional data. But there are a number of approaches out there that can be used. They do require training a model on image features, but still we can then develop a statistical test to figure out whether two distributions, two populations seem to be the same or not. So then with this trained statistical test, we can then examine whether there is a distribution shift or whether there seems to be no distribution shift in our real-world data. And if there is a distribution shift, then this can be used to trigger some corrective action or some escalation process within the manufacturer's post-market surveillance strategy. So this approach is relatively straightforward. It is agnostic of the model itself. So we don't, at this point, we don't know what machine learning model was used. It does work well on high-dimensional data, but there are some major weaknesses with this. We can detect when there was a distribution shift, so we can see that something changed, but we don't really know whether this impacted performance or not. And we also don't really know what happened actually. So what was the change? We just know there was a change, but this doesn't really, so the root cause identification needs to happen then after separately. And there is actually also work out there in the meantime that tries to detect such shifts in the deployment scenario, while at the same time also trying to investigate the root cause. Is it due to maybe a change in prevalence of the disease? Is it due to maybe change in imaging setting or similar? There's a lot of work, I think, still to be done in that area. But I think there is a lot of room for improving the monitoring of model performance to, again, enhance trust in the model. Yeah, so coming back to the topic of this talk. So the promise of XAI is that it will allow us to understand deep learning models. And I think it does that to an extent, but I think the most helpful application at the moment is to really expose failure modes. I think XAI can be very good at exposing failure modes, maybe not so much directly letting us understand the mechanism, but it's still, I think, something valuable. But then again, so many explanation techniques are approximation of what's actually happening. And then it really depends on which technique you use, what kind of explanation you get, which kind of questions their applicability. And as I also mentioned, the usefulness of the explanation really depends on the application context and how people interact with the explanation. And yeah, so I'm a strong advocate for inherently interpretable models that address some of the weaknesses of these post-hoc explanation approaches. And I do think that it's very easy to ask for interpretability, but there are alternative ways to enhance the transparency of neural networks through validation and monitoring. Yes, with that, I want to end my talk. I thank you very much. And these are my funders and my co-authors. And yeah, I welcome your questions now.
Wonderful, dear Lisa. Now you get a lot of virtual applause here. Definitely also from my end. Let me see. Here you are. Fantastic. All right. So please not only clap, but also raise your hand or write your comment or question directly in the chat. Maybe this is also the time, or maybe it already happened that we stop the recording.